Is it jibber jabbering? Yada yada yada. I will begin with a word of prayer. Dear Father, we thank you for this day again, Lord. I thank you for the students. We thank you again, Lord, that we have your righteousness rather than our own if we accept you, and the gift that you freely give us if we follow you, Lord Jesus. And we just thank you for this class. Just pray you again guide our steps, Lord. In your name I pray. Amen. All right, so as you guys know, we are in chapter 12. As you also, now see, I'm just fighting with these. So I read chapter 12 yesterday, and I think a lot of the arguments are nearly understandable, and I mean just without even. What I mean is you can just read them and kind of have a sense. It makes sense, all right? I mean, some things in a math book you're just going to have to get. You have to write out, right? I mean, that's just the nature of the beast. I'll put it over here, but this is Theorem 4. What it is?
I think it's too zoomed in.
Is it too zoomed in now?
It'll be okay. It'll be okay.
Yeah, it'll be fine. So let R be a PID and M a Oh, okay. M a free R module of finite rank n. Also, let n be a submodule. Man, this board's shaking, drives me nuts. Then, number 1, n is free of rank, excuse me, m, and m is less than or equal to n. Why not make the rank of m m and make the rank of n n? I'm not going to change it because then I'll somehow injure something else here too. It bothers me. There exists a basis y1, y2, dot 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 y n of m such that a1, y1, a2, y2, am, ym is a basis for n. And the a1, a2, am are non-zero elements with divisibility relations. A1 divides A2 divides AM. Okay, so this is Theorem 4. And it takes him some work there, about a whole page and a half to prove this thing, right? Eventually, though, that leads us to the thing I'm actually interested in, which I guess I'll put over here, Theorem 5, which I probably should have started with. Oh well. Let R be a PID. And yeah, this is the one I actually wanted to start with. I'm sorry, guys, my bad. M a finitely generated R module All right, there we go. This is what I wanted. Then number 1, M is isomorphic to r to the r power, direct sum r mod A1, direct sum r mod the principal ideal generated by A2, direct sum r mod the principal ideal generated by AM. For some r greater than or equal to 0, an integer, and non-zero. And what do these a's satisfy? They have the divisibility relations. A1 divides A2 divides AM. This thing I just wrote down is the fundamental theorem of existence in the invariant factor form. There's more to it. That's part 1. Part 2, M is torsion free. If and only if M is free. And 3, tor of M is isomorphic to the piece that's the not the r to the r piece, everything else but that. All right. He says, in particular, M is a torsion module if and only if r equals to 0. And in this case, the annihilator of M is the ideal AM. So what's the annihilator of M? Do you guys remember? I don't think I ever wrote it on the board. There's that pesky, yeah, way a few pages back in here. Annihilator of M would be R and R, such that Rm equal to 0 for all M and M. So the annihilator is the ideal of the ring which kills everything in the module. So if the torsion is 0, that means that there is no such thing. All right, so if torsion is 0, let's just, a couple of kind of dramatic cases, if you will. So special cases, right? Number 1, M is isomorphic to r to the r, then M is free. Rank of M is equal to R. And this is also called the what? The Betti number. So if free module, well, yeah, even when R is not free, that's still called the Betti number. Even if there's a torsion piece, the dimension of the free part of the module is still said to be the Betti number. All right? So it means always the case that R is the Betti number. So if this is the case, so you can see that the torsion of M is isomorphic to 0 by comparison. Right? If you have this decomposition and it's equal to r to the r, then this piece apparently is gone, which is to say that the torsion, that's the torsion piece, all right? Now I'm using something which is the uniqueness. The uniqueness part of the theorem says that if you have an R module decomposed like this, if you have the invariant factor decomposition as such, if you have another invariant factor decomposition of the same module, all right, then those invariant the decompositions are going to be unique. It's like you're not going to find two different invariant factor decompositions, one with a different R here. Like this R is a unique thing, and the structure of the torsion piece is also unique. This is proved. That takes some work, which I'm not going to do. You'll forgive me. The other case here, of course, would be what? Another special case would be when R is equal to 0, right? So M is just isomorphic to the torsion of M, right? So in that case, it's R mod A1 direct sum R mod AN M, I guess. So in this case, the module is said to be pure torsion. All right. So let's think about some examples. All right. So first of all, one of the modules we talked about was the fx module, right? So example 1. Remember, if we had a linear transformation t from v to v, where v is finite dimensional over some field, then we defined, how do we made v and fx module. How did we do it? Remember, we said f of x acting on v was by definition what? Right. So with the understanding of what this means, we look at the f of t and let that act on v instead. Exactly, that's how we did it. And that defined an fx module. Right? So, here R equals to fx, right? Is that a PID? Yes, polynomials over a field are a principal ideal domain. This we know, which means that Theorem 5 applies, right? So there is going to be a invariant factor decomposition of the fx module, right? Now think about this. What if it was not pure torsion? What if we had that v, v is going to be what? Isomorphic to r to the r, direct sum r a1 and so forth, right? I actually want to get into the details of how we calculate this, but suppose for a second that r was non-zero, little r. If r is not equal to 0, what would that say about v? What would r non-zero mean here? That would mean that v is isomorphic to the direct sum of some Cartesian product of polynomials over the field with some other piece. What's the dimension of polynomials over a field? I'll tell you what it's not. It's not finite. But we assume v was finite dimensional, right? Therefore, r cannot be zero, non-zero rather. If r is non-zero, then this is crazy. We'd have a finite dimensional thing is isomorphic to an infinite dimensional thing, right? Therefore, the VT module is pure torsion. Right? And I'm gonna work on describing how we calculate that as we go on, okay? But before I get back into how we actually, okay, so it's pure torsion. The question that remains is how do we actually describe this? What is that, okay? We'll get back to that. But let's look at a second example, which is a little bit different. example 2, we could have something like m is equal to, I don't know, how about z, I don't know, z900 Cartesian product with z300, something like that. Oh, and we could throw in a z2 while we're at it. So here, this would be a z module, right? I've done something kind of silly. I've given it to you. Maybe it's already in an invariant factor form. I'm not sure. Well, I mean, fine. First of all, we could do this, right? Agree? We can swap the order of factors around. That's an isomorphism. Yeah?
Why are you putting the 2 at the top?
That's z2 cross z2. No, z2 is, oh, did I say z2 cross z2? Z cross z. Thank you. Eventually I'll get it right. All right, so with that, we can use Theorem 5, and you can tell me what's the torsion and what's the free part of this module. Right? Torm is what? Up to isomorphism, it is z300 cross z900. Right? Which, of course, Dr. Smith would be happier if we had written like this, right? Z mod 300z direct sum z mod 900z, right? I mean, that is what that is, after all. And in fact, we can do better than that still, right? What is that really? It's z mod the principal ideal generated by 300, direct sum z mod the principal ideal generated by 900 over the integers. Yeah? Does this make sense so far? Yeah?
A couple of seconds ago, you said that it might be already in that form. Does that mean like there's certain numbers that would
To
make
be-
it not already in that form?
Yes,
Or-
yes. If the divisibility relations weren't already happening. So, and also, just to be picky, Theorem 5 has got the free piece first, and then it's got the torsion piece, and it has the torsion piece arranged so that the annihilator comes last. In contrast, if we look back at chapter 5, where the fundamental theorem of finitely generated abelian groups is stated, or as we said last time, there they have it arranged from like largest to smallest for convenience of like calculation. Whereas here it's arranged from smallest to largest for convenience of logic. So there's a reordering that you have to do if you want to compare the invariant factor decomposition in chapter 5 of Dummett and Foote versus the invariant factor decomposition of chapter 12. But this is not a big deal. You'll figure this out. Anyway, so does this make sense? I mean, I think this, so here, this is my A1 is 300. My A2 is 900. Does 300 divide 900? Okay, so divisibility relation satisfied, and the Betty number here is 2. So this module is neither free nor pure torsion. It's got a little bit of both, right? Does that make sense? Now, let's example 3. Let's see, Z300, what can we do with that? That's what? That's Z of 3 times 5 squared times 2 squared, isn't it? So you could break that into what? That's really a z3 direct sum with a z25, direct sum with a z what? 4. Am I wrong? So what I'm trying to say is, instead of being given that 300, we might have been given a, it could have looked like this, right? It could have looked like, you could have given n equal to, z2 cross z3 cross z25 cross z4 cross z900, and that would not have yet been an invariant factor decomposition. I mean, it's isomorphic, sure, but to be picky, you have to put all this stuff together as being that Z300, because you need those divisibility relations to have invariant factor decomposition. All right? Now, moving along. You can do what? Well, we're in a principal ideal domain, which is also a what? A PID is also a. This was a gateway drug for Theorem 5, right? I mean, this is like Theorem 5 in a concrete context. This is Theorem 5 happening under the umbrella of it's happening in the context of a free module. So that like the proof of Theorem 5 involves using Theorem 4 and like bootstrapping from the arbitrarily finitely generated thing into that concrete context, using Theorem 4, and then kind of ripping your way back to the abstract finitely generated Noetherian module. But I don't want to get into those details. I really don't. So I shouldn't have written that. I wasted valuable class time with it. But PID implies UFD, right? And so if we look at A, as in any one of those, let me just use A for a generic one of these invariant divisors. By the way, the A1 through AM are called the invariant. I think they're called the invariant factors. Yeah, these are the invariant factors, I should mention. So the result that I'm trying to discuss at the moment is that if you give me the Betti number and if you give me the invariant factors, right, that uniquely describes the invariant factor decomposition of the module. And that's unique, all right? Like there's one of those to be found for a given finitely generated R module. But having said that, if we take these elements of the ring, A, right, they're non-zero elements in a PID, which is also UFD, so there exist what? Prime power components, right? I can write it as a unit times P1 to the alpha 1, P2 to the alpha 2, PS to the alpha S, where what? Where P1, P2, PS are distinct primes in the ring, right? And so then what that leads you to is the understanding that if we look at R mod, the principal ideal generated by this A, well, that's going to be isomorphic to, by the Chinese remainder theorem, the following. It's going to be the direct sum of the P primary components, like so. All right. So what that's saying is if we had the prime decomposition of the invariant factors, well, then we can take the invariant, each one of these invariant factors and the pieces in the torsion and we can subdivide that according to the prime decomposition of the invariant factor. So I just did this for Z300, right? I just exhibited this for Z300 over here. I'll write it over here though. So like Z, so 300, right, is equal to Z mod, what is it? 3 times 5 squared times 2 squared, right? And that is up to isomorphism, Z mod 3Z. So let me use the other notation. 3 Z 5 squared Z 2 squared, yeah? Now I'm struggling with the notation. um, okay, so yeah, great, googly moogly. Wait, no! Theorem 6, the world's going to end. Let's see here. Theorem 6, fundamental theorem, elementary divisor form. So again, R a PID, M finitely generated R module. All right. Then M has the following decomposition. It can be written as a free part, direct sum with R mod P1 to the alpha 1, R mod P2 to the alpha 2, and then R mod PT to the alpha T, where R is an integer greater than or equal to 0, and P1 to the alpha 1, P2 to the alpha 2. Let me just say it this way, P1, P2, PT are primes, and we're assuming alpha 1, alpha 2, alpha T are positive integers. Now, here's the thing that got me. Well, it didn't really get me, but the thing I wanted to say, to emphasize here, and just over there, I was assuming that the primes were distinct, right? Because that's the prime decomposition of something in a UFD, right? I make no such assumption in this theorem. Possibly, you know, not necessarily distinct. So we have, and this is the so-called elementary divisor form of the decomposition of an R module, finitely generated R module. We have these two competing viewpoints. We could either find a invariant factor decomposition of it, or we could find a elementary divisor decomposition of it. Let's see here. This is neither at the moment. So to fix my example 3 continued, so we had n equal to z2 cross z3 cross z25 cross z4 cross z900. All right. Then the thing is, I do this. This is isomorphic to, of course, z2 cross z3 cross z25 cross z4, and then this 900 breaks up how? You got what? You got a z3 squared cross z5 squared cross z2 squared, right? 4 times 5 times 9 is 900. And then this is almost the elementary, I mean, this is where you kind of be I mean, if a student gave you this on the exam and you said, no, that's not the elementary divisor form, you kind of be being a jerk at that point. But maybe we should insist that we reorder things, right? So you got z2, and then you got like the z3 piece, which would be z3 cross what? Well, actually, no. I mean, I really can't complain at this point. I mean, no. I mean, I have to take that back. I walk that back for a second here. I mean, I'd just be wrong if I counted it wrong, because it already is. There it is. I mean, that's an elementary divisor decomposition of the R module. Notice there's no divisibility assumed amongst the different components. But on the flip side of things, we do insist that they're all prime powers. Okay, now you can uniquely go, if I give you a list of invariant factors, there's an interchange here. You can go from elementary divisors, multiset of elementary divisors is interchangeable with the list of invariant factors. All right. You can go from one to the other and from the other to the one. We'll see that. So the but if you could collect all of the prime powers. You could collect them all into one thing, and then that would be the p primary component. Like, that's another thing you can do. You could collect. I could collect like this and this together, and z3 cross z3 squared. This would be the 3 primary component of the module. I could collect the pieces with 5, like the z5 squared cross z5 squared together. That would be the 5 primary component of the module. I could collect the 2 pieces together. That would give me the 2 primary components of the module. I'm mostly telling this to whichever one of you is doing the CELO theorem, because this is related to the CELO P groups. There's like an interplay between this and the CELO theorem, which we will hear talk about later in this semester. Okay, so you see we have 2 different what's the word? Kinds of decompositions, and we can go from one to the other once we understand. Yeah. Now I have a slide that I have a whole caboodle of examples of this claim that I'd like to show you, rather than trying to do one off the fly here. What I'm going to spend the remaining time on is trying to explain specifically how these ideas play out for a linear transformation. All right? So let's focus our attention on the VT module. You're right. Take a linear transformation T from a vector space V to a vector space V. We're going to focus on that, all right? And the FX module. So again, our fundamental definition was that f of x acting on v was defined to be f of t acting on v, right? For all f of x in the polynomials over the field, and v in the vector space v, right? We have already argued that it's pure torsion, right? We've already argued that it's pure torsion. And now what we want to do is try to see if we can understand what that AM is. That's the next goal. Okay, so apparently V is, V is M here, okay? M is isomorphic to something like R mod A1, direct sum R mod A2. We'd like to figure out how to find these A1 through AM, but here what? A1 divides A2 and so forth divides AM, and each A1, A2, AM are what? These are polynomials. What is the largest invariant factor here? Remember? AM is the annihilator, right? It's the annihilator of M. What does that mean? It means, well, that doesn't quite make sense, does it? You're like, wait a minute, flag on the play. A second ago, you told me that the annihilator of M, sorry, I watched football yesterday, some lingering sports terminology. I'll get it out of me soon. Man, that was a boring game. It was just, just so boring. Very boring. Anyway, I really regret not doing math with that time, but anyway, so it would seem to be a set of things, right? But we're talking about a set of polynomials, and, well, oh, I'm sorry. This is I've lost. I know what it is. I forgot this. This isn't supposed to. The principal ideal generated by AM should be the annihilator. That's what I should say. So what we're looking for is the monic polynomial, without loss of generality. Let's look for the monic polynomial of least degree, which generates that. Right. That would be the annihilator, the generator of the annihilator. All right. So we're looking for something of the form. So some f of x and f of x such that f of t on v is equal to 0 for all what? For all v and v. Right? So, definition, if m of x well, I don't know, some notation. definition, min t of x is the monic polynomial of least degree for which min, I'm really tired of this notation already. Let me just call it m. For which m of t equal to 0. So this is the so-called minimal polynomial for t. Minimal polynomial. So to understand the structure of the fx module for a given linear transformation, this vt module, we need to find the minimal polynomial. That gives us the largest invariant factor. All right. Now, the theorem is, so I'm jumping ahead a little bit here. We can also talk about the characteristic polynomial. The characteristic polynomial t of x is equal to, and this is differing from my linear notes just a little bit, but it's the determinant of x times the identity for v minus t. So this is the characteristic polynomial. All right? So here's the theorem. Has same factors as m of x. So this kind of tells you something about how we're going to calculate things. Shouldn't really tell you too much. So we need some kind of calculational scheme to figure out these a1 through ax. All right. I mean, how do you actually find those, and what does that look like? All right. And I have asked you things about the rational canonical form for a matrix, right? What does that have to do with this, right? Well, it has everything to do with this. It turns out, once we sort through this, this is like directly tied to the rational canonical form, all right? So let me just show you hypothetical. I actually have many examples to add to Dumb Input. I have a PDF I need to post for you guys. I finally found it yesterday. But here's the algorithm. And this is Theorem 21. And I don't know which section it's in. It's not in 12.1, obviously. I think it's in 12.2. And there, we get this pretty neat so I'm skipping ahead a bit. This section 12.2 proves the things I just said and it sets them in a good context. But this is Theorem 21 on page 479. And what it says is simply this. You can take a minus, I think it is, xi, right? So, and this is for, you want to think about the matrix of the transformation you're studying. So suppose the transformation you're studying has matrix A. So the invariant factors for the matrix are the same as the invariant factors for the transformation. So if you can calculate it for the matrix, you've calculated it for the transformation. But what you do is you take the matrix and you subtract xi like that, and then you do row and column operations. And eventually, it gets into the form 1, 1, a1 of x, a2 of x, dot, 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 am of x. So by doing row and column operations to the matrix of the linear transformation in a very systematic way, it will reveal the invariant factors, just like that. For a stupid example, if I had a equals to like 3, 0, 0, 4, and I did this business, a minus, so if I looked at, and I'm not actually going to do it because we don't have, oh, dang it, I think, eventually, it doesn't matter, but I really should be looking at xi minus a to make it less weird. So that would be x minus 3, 0, 0, x minus 4. So through the row and column operations, which I will explain more carefully next class, you can simplify this one to 1, x minus 3, x minus 4. And what that means is that the minimal polynomial of a is this. This is the a1 of x. If you plug the matrix into that, if you do a minus 3i times a minus 4i, it multiplies to 0. It's the 0 matrix. If you had something like 3, 3, 3, 4, 4, right, and you look at xi minus that, it will simplify to 1, 1, 1, 1, and then still x minus 3 times x minus 4. It's got nothing to do with it being 2 by 2. It's because this matrix is always already diagonalizable. It's diagonalized, and so for a diagonalizable matrix, the minimal polynomial is got one linear factor for each prime. Just one. So anyway, I will try to explain the rational canonical form and how we actually calculate this. I'll actually show you some explicit examples of this. The cool thing is, almost the same calculation will show us how to take a finitely generated abelian group, look at its matrix, and do almost the same steps. It will reveal to us like the simple form of the generators and relations, and from that we'll be able to read all, get a form that's like example 2. So the other kind of example we'll look at is something like this, like G equals to A, B, C, such that, 2A equals to 0, and A plus B plus C equals to 0. So this right here is a finitely presented abelian group. You can write down a relations matrix for it, and then do like zero operations on that in order to refine the relations into their simplest form and reveal the true structure of the group. We also get that at the same time. And then I think I also should talk about the elementary divisor form has a connection to the we have to assume that all of our eigenvalues are in the field, but if we do that, then the elementary divisor form is essentially the Jordan form when we look at the matrix. So there's some sort of interplay between these ideas. But I'll try to, I have lots of examples to show you next time about these things. So anyway, thanks. And I think I owe you the calculation of the knot. So if we look at that knot, we can actually write down equations like this to describe the crossings and things, and then use that thing I'm talking about to solve it. But one day at a time. Yep.